let us now move on to our next chapter on polynomials. In this video, however, we will be covering a few basic definitions related to polynomials and also see what are the conditions that should be satisfied in order for an algebraic expression to be called as a polynomial. And we will also see different types of polynomials and several definitions related to polynomials. Okay, and then in subsequent videos we will extend those ideas and solve some problems using polynomials. And going forward, we will also be doing several important concepts using polynomials. Okay, so let us dive into this and begin our discussion. Basically, a polynomial is an algebraic expression which satisfies some conditions. So we are familiar with algebraic expressions from our previous classes. An algebraic expression is basically an equation containing one or more variables. For example, in this case, we have an algebraic expression called 4x. So this is an expression in a single variable, and the variable is x. Another expression here is 3y. So this is an algebraic expression, and the variable involved here is the variable y. So it is an expression in a single variable. Similarly, here the variable is z, and it's half z. The expression itself is 1 by 2 z, or we can write it as 0.5 z because 1 by 2 is 0.5. And here we have minus x is the same as minus 1x. So again, this is an algebraic expression where the variable is x, and in this case the variable is z. So basically, the variable is denoted by some symbol, and usually we use some letters to represent the variables, and it is a general norm to use the variables x, y, z, w, and so on to represent variables. Okay, so what we noticed in the previous examples is that all of them have only one variable. So these are basically polynomials in a single variable. So these are all examples of polynomials that contain only one variable. Now, the other thing that we notice is that all of these polynomials have a general form of a constant times a variable. So this is 4 times x. So the number 4 is the constant and the x is the variable. So in 4x, the constant is 4 and the variable is x. Similarly, in this expression 3y, the constant is 3 and the variable is y. And in the expression half z, the constant is half or 0.5 and the variable is z. And similarly, in the expression minus x, the constant term is minus 1. So the multiplying factor here for minus x is minus 1. So minus x can be written as minus 1x. If it was plus x, we can write it as 1x. So we don't write the 1 because it's understood. Okay, so in the case of minus x, the constant that is multiplying the variable is minus 1 and the variable itself is x. So in general, what we see is that the polynomial in a single variable has a general form as some constant times the variable as ax. So a is the constant and x is the variable, or we can call the constant by a different name, b, and the variable by a different letter y, so by or cz, and so on. So generally we use the letters towards the end of the English alphabet as the variables, and the letters towards the starting of the alphabet like a, b, c as the constants. Okay, so polynomial with a single variable has the general form of a constant times a variable. Now, we further have other types of expressions. Here again we have expressions which are containing only a single variable, but we now have more terms. So for example, 2x is having a single term and a single variable, so it's only one term 2x and the variable is x. In this case we have two terms, so x squared and 2x, and the entire expression has only one variable. Again, it is only x, there is no other letter there. So therefore all these belong to polynomials category that contain only one variable, and the single variable that is present in all these polynomials is the variable x. Similarly, in this particular case, we have more terms, but the variable is a single variable, which is y. Here also the variable is a single variable, which is y. Here also it's a single variable, which is y. So all these are examples of polynomials that contain only one variable. The number of terms may differ, but the number of variables in all these cases is just one variable. Therefore, these are polynomials that contain only a single variable. The next thing that we notice from the examples that we have seen so far is that all of the polynomial expressions have the powers or the exponents of the variable given by whole numbers. So if you look at each of these examples, the power on the variable x is 1. It's 2x is basically 2x power 1. So in this case here, x power 2 plus 2x power 1. So the power here is 2 and the power here is 1. Similarly, in this particular example for a polynomial, we have x power 5, so the power here is 5, and here it's minus x power 2, so the power is 2. 3x is nothing but 3x power 1, so the power is 1. And 4 is a constant. The constant can be written as 4x power 0. X power 0 is 1, so 4 into 1 will remain 4. So the constant term is basically having a variable x with a power of 0. But nonetheless, what we notice is that in each and every case, in each and every example, the exponent or the power of the variable are all whole numbers. So all the powers are whole numbers. So this is one requirement for an algebraic expression to be called as a polynomial. So for a polynomial, it is required that all the exponents are whole numbers. So if any of the term in the polynomial has an exponent that is not a whole number, then that expression cannot be called as a polynomial. It will not be a polynomial. So let's look at some examples of algebraic expressions which are not polynomials. So here we have the expression square root of x plus 3, and of course square root of x is nothing but x power half. So in terms of the exponent, we can write square root as power half. So it is x power half plus 3. Similarly, another example here is x plus 1 by x. So if you take the x to the numerator, it becomes x power minus 1. So it's x plus 1 x power minus 1. And then we have the cube root of y plus y square. So the cube root of y is y power 1 by 3 plus y square. So we see that there is at least one term in these expressions where the exponent or the power is not a whole number. So here the power is 1 by 2. 1 by 2 is not a whole number. Whole numbers are 0, 1, 2, 3, 4, 5, and so on and so forth. So 1 by 2 is not a whole number. Similarly, in the second example here, we have a term where the power of the variable x is minus 1, x power minus 1. So minus 1 again is not a whole number. Similarly, in the third example, we have y power 1 by 3. 1 by 3 is also not a whole number. So each of these algebraic expressions have some terms whose exponents or powers are not whole numbers, and therefore these expressions are not polynomials. Okay, so this is something that we have to remember. For a polynomial, all the terms in the algebraic expression must have exponents or the powers which are whole numbers. If even a single term has a power that is not a whole number, then that algebraic expression is not a polynomial. Okay, let's look at another type of polynomials where we have only a constant term. For example, in our previous case, we had the number 4 belonging to the polynomial expression, and similarly we had minus 3 here belonging to the polynomial expression, and 2 here. What if we had that constant numbers as a standalone element of the polynomial? So if we have just the number which is a constant and non-zero, then what will be the power of the variable for that, and can we call this as a polynomial? So the constant number can be written as the constant times x power 0, and x power 0, anything power 0 is 1, we know that. So any of these constants can be written as the constant multiplied with x power 0. Anything multiplied by 1 will be itself. So 2 is basically 2 times x power 0, and x power 0 is 1, so we get simply 2 here. So 2 is 2x power 0, minus 4 is minus 4x power 0. Similarly, 6 is 6x power 0, and 1 by 3 is 1 by 3x power 0. So in all these cases, we notice that the exponent or the power of the variable in the algebraic expression is 0, and 0 is a whole number. So therefore, all these terms are polynomials, and we call them as constant polynomials. The reason we call them as constant polynomials is because their values will not change. Okay, so 2 will always remain as 2, minus 4 will remain as minus 4, because the multiplying variable here is x power 0, which is always equal to 1 irrespective of the value of x. Okay, so we call such numbers which are non-zero constants as constant polynomials. Similarly, if we have the number 0 itself, then we call this as the zero polynomial. So 0 can be written as 0 x power 0. So 0 into x power 0 is 1. So 0 into 0 will be 0 into 1 will still be 0. So if we have simply 0, we call this as the zero polynomial. Okay, so that's a few definitions. Let's move on to the next definition in terms of the number of terms that are present in the polynomial. So based on the number of terms in the polynomial, we can classify the polynomials into various types, and they have various names depending on the number of terms that are present in the polynomial. So let's look at some examples and try to understand what we mean by the terms in the polynomial. So we have, let's look at this example, x squared plus 2x. So that's in this particular polynomial, there are two terms. The first term is x squared. So x squared is excuse me, x squared is one term, and 2x is another term. So there are two terms in this first example of the polynomial. Similarly, if you look at this particular expression, it's a polynomial in a single variable, and the variable here is y. Instead of x, we have y. But the entire expression has only y, so it is a polynomial in a single variable y, and it has how many terms? 3 terms. Y cube is one term, 3y minus 3y square is another term, and 6y is the third term. So there are 3 terms. So each of these is called as the term of the polynomial. And in general, a polynomial can have any number of terms. Of course, the number of terms should be finite. You cannot have an infinite number of terms. It can be some very large number of terms also, but it should be countable or finite. So we have an example here of a polynomial which has 101 terms. So, okay, starting from x power 100 to x power plus x power 99 plus x power 98 and so on and so forth, up to x power 1 plus 1 x power 0. So from 1 to 100 we have 100 terms, and the x power 0 term is the 101st term. So we have here a polynomial with a total of 101 terms. Similarly, we can have a polynomial with any number of terms as long as the total number of terms is finite. Now, depending on the number of terms that a polynomial has, we have a few definitions here. The first definition is called as the monomial, and the monomial, as the name suggests, mono means one. So monomial means it's a polynomial that has only one term. So if the polynomial has only one term, like this case 2x or 3x squared, so it's a single term 2x. This is a polynomial which is a single term 3x squared. This is a polynomial which is a single term minus 5x cubed. So the only term here is this 7x power 8. Whatever is the power, the exponent, it doesn't matter, but there is only one single term in this polynomial. Similarly, we have this constant polynomial. It's 5x power 0. So we simply write that as 5. Or we can have another polynomial in a variable y as y power 4. So that's a single term. 3t power 6 is a single term, or 4u power 5 is only a single term. So only the variables have changed. We have y, t, or u, or you can have z, whatever. Okay, so in all these cases we have only a single term in the polynomial expression, so therefore these polynomials are called as monomials. Okay, similarly, binomials are polynomials that have only two terms. So if you have an algebraic expression which is a polynomial and it contains only two terms, then it's called as a binomial. So for example here, x squared minus 2x, it has one term x squared and another term minus 2x. Y cubed minus 1, one term is y cubed, the other term is minus 1. Similarly here is minus 4t squared plus 2t. 4t square, 4t square plus 2t. 4t square is one term and 2t is the other term, so there are two terms. So similarly here, the polynomial in the variable u, it is having one term u power 10 and the second term is minus u power 3, so it has only two terms. Again, this is also a binomial. Similarly, if the polynomial has three terms, we will call it as a trinomial. Again, it has three terms and one of the terms can be the constant term. So like we have 1 here, or we have minus pi here, or root 2 here. So now we can have the constant term to be any number. The only thing that the polynomial should satisfy is the power terms, the exponents should be whole numbers. The other numbers can be any numbers, it doesn't matter. As long as all the exponents in the polynomial are whole numbers, we will call it as a polynomial. And when the polynomial has only three terms, we call it as a trinomial. So we have three terms. One term is x squared, the other term is minus 2x, then the third term is plus 1. Let's look at this. The first term is minus 2t squared, the second term is plus 3t, and the third term is minus pi. So it has three terms. So similarly here, u power 50 is one term, minus u power 3 is the second term, and square root of 2 is the third term. So we have three terms here. So all these are examples of trinomials. So let us move on to the next set of definition, and that is called as the coefficients of the polynomial. So every polynomial has some terms, and each term of the polynomial has a multiplying factor. That means there is a constant number multiplying the variable, and that constant is called as the coefficient of that particular term of the polynomial. So basically each term of the polynomial has a coefficient. So if you look at this particular polynomial, we will write the coefficients of each of the terms of this polynomial. So for the first term, which is minus 2x power 4, the constant that is multiplying the term, the x power 4, is minus 2. So the coefficient of x power 4 is minus 2, because minus 2 is the constant that is getting multiplied with x power 4. So the coefficient of x power 4 is minus 2. Similarly, the coefficient of x power 3 is plus 3, because we have x power 3 getting multiplied with 3. So that's the 3 here is the coefficient of x power 3. Similarly, the coefficient of x square is the number 4. It is plus 4, so we'll simply write it as 4. The coefficient of minus x is basically the coefficient of x power 1. What we have here is a minus in front, so it's minus 1x. So the coefficient of x is minus 1. And the coefficient of x power 0, if you look at the expression, you don't see x power 0 here, but we have seen earlier that the constant term can be seen as getting multiplied with the variable x power 0, because x power 0 is 1. So minus 2, we can write that minus 2 as minus 2x power 0. So the coefficient of x power 0 is minus 2. So let's write that down here. Coefficient of x power 0 is minus 2. Okay. So now we know the next definition, which is the coefficients of the polynomial. And what we know is that every term of the polynomial has a coefficient, and the coefficient is basically the constant number that is multiplied with the variable part of the polynomial term. Okay, so the next definition that we have here is the degree of the polynomial. And what do we mean by the degree of the polynomial? So when we have a polynomial expression, the degree of the polynomial is the highest power of the variable in the polynomial. So let's look at an example and it will become very clear. So if you have a polynomial here given by this expression, we have it as 4x power 8 minus 2x power 4 plus 6x squared minus 1. The degree is nothing but the highest power of the variable. The variable of this polynomial is x. So the highest power or the exponent of that variable is the number 8. So we have x power 8 here, x power 4 here, x power 2 here, and x power 0 here. Constant term is x power 0. So the highest power or the highest exponent in the expression for the variable x is 8. So hence the degree of this polynomial is 8. Okay, so this is what we mean by the degree of the polynomial. Degree of the polynomial is the highest power of the variable in that particular polynomial expression. So similarly, if we look at this example here, so we have 2y plus 6y square minus 3y power 4 plus 0.5y power 5. So what is the degree of this particular polynomial? The degree, as we defined, is the highest power of the variable. So the highest power here is the number 5. So we have power 1 for this. 2y is 2y power 1, 6y square is y power 2, y power 4, and we have y power 5 here. So okay, the coefficient does not matter. The degree concerns only with the power of the variable. The highest power of the variable gives us the degree, and as long as the coefficient for the highest power is not 0, that will be our degree. If this coefficient is 0, then this entire term will disappear and the degree will be something smaller. Okay, so the degree of the polynomial is the highest exponent or the highest power of the variable. So in this particular case, the highest power is 5, and therefore the degree of this polynomial is 5. So this has a degree equal to 5 because the highest power here is 5. Okay. Now, what is the degree of a non-zero constant polynomial? So if we have just a constant like the number 5 or like the number 2 or minus 2, the constant term is basically the number multiplied with x power 0. Again, this is something which we have seen just a few minutes back. So now 5 is nothing but 5x power 0. Similarly, minus 2 is nothing but minus 2x power 0. 1 by 3 is 1 by 3 times x power 0, right? So if we have a polynomial containing only the constant term, then the constant term has a variable with a power of 0. So therefore, the highest power for the constant polynomial, which is a non-zero constant polynomial, is going to be 0, and therefore the degree of the polynomial is also 0. Okay, so the degree of the constant polynomial is 0. However, if the constant itself is 0, for instead of 5, if we have 0, we can't say 0 x power 0 and say the degree is 0. Okay, that means that term doesn't exist at all, and therefore we say that the degree of the 0 polynomial is undefined. Okay, so if we have just a number 0, we cannot say this is 0 x power 0. It makes no sense. So therefore we simply say that the degree of the 0 polynomial is undefined. Okay, there is no degree for the 0 polynomial. Okay, but if it's a non-zero constant polynomial, then the degree for the non-zero constant polynomial is 0. Okay, but for the 0 polynomial itself, the degree is undefined. Now, in general, when we write a polynomial expression in a particular variable x or y or z or t or u, we can simply denote that expression as some function. Okay, like we have put here, it's a function of x, p of x or q of x or f of x or something like that. Okay, so the polynomial expression, we can represent that or denote that by some function of x. We say this is a function of x. It is a polynomial in the variable x and it has this form. Similarly, we can say another polynomial in the variable t or y or z, right? So this is a polynomial in the variable t and has this form, minus 3t squared plus 2t. So we can denote that as p of t or q of t or f of t, whatever. Similarly, here we have a polynomial in the variable u, which we denote as f of u. We could have denoted that as p of u or q of u or r of u, whatever name we want to give. But in general, what we can do is we can represent a polynomial expression as a function of that particular variable. So we just say that this is a polynomial which is a function of the variable u. It's a polynomial which is a function of the variable t. This is a polynomial which is a function of the variable x, and the function itself we can call it as p, q, r, f, whatever term you want. Okay, so this is again a notation that you should be familiar with, because later on we will be using this kind of notation to represent our polynomials. The next definition of a polynomial is what is called as the linear polynomial, and a polynomial is linear if the degree of the polynomial is 1. So a linear polynomial is a degree 1 polynomial. That means the highest power of the variable in the polynomial is 1. That's why we say it has a degree 1. So if you look at these examples here, 2x plus 1, the highest power of the variable is 1. It's 2x power 1. So again here 5x is a single term for the polynomial, and the power of the x is 1. So the highest power is simply 1, and therefore this is also a linear polynomial because the degree of this polynomial is 1. And similarly here we have minus 2x minus 3, so the power to the variable x is 1, so therefore this is also a linear polynomial. And what we notice here for the linear polynomial is that it can have a maximum of only 2 terms. So if you look at these examples, this example for the linear polynomial has 2 terms. 2x is one term and 1 is the other term. In this case also minus 2x is one term and minus 3 is the second term. But in this case there is only one term, which is 5x. Okay, so what we see is that the linear polynomial can have at most means a maximum of only 2 terms. So a linear polynomial has at most 2 terms, and the general form of the linear polynomial is ax plus b. So a is the constant, like we have 2x plus 1, so 2 corresponds to the a and the 1 corresponds to the b. So it's ax plus b, it is 2x plus 1. Similarly, 5x can be thought of as ax, so a is 5 plus b, the b value is 0 in this case, so it is 5x plus 0, so 0 we don't write it, so we leave it as it is, so we simply have 5x. That basically means that this b parameter in this expression, in this polynomial, is 0. So the general form of a linear polynomial will take the form of ax plus b, where a and b are some constants and the parameter a is not equal to 0. If a becomes 0, then the x term itself will disappear and we will be left only with the constant term, which will have a power of 0. But we want the polynomial to be of degree 1. If the a becomes 0, the degree 1 term will completely disappear and the degree of the polynomial will go below 1. So therefore, the condition for the constants a and b is that a and b are both constants and a is not equal to 0. That is, the coefficient of the highest power must not be 0. Otherwise, the degree will become less than that particular power, right? So we want the polynomial to be of degree 1. So that means the coefficient of x power 1 must be non-zero. Okay, so this is the linear polynomial. Similarly, we can have a quadratic polynomial, which is a polynomial of degree 2. That means the highest power of the variable is 2. So like we have in this example, a polynomial where the highest power of the variable x is 2. Similarly here the highest power is 2, the highest power here is 2. The other terms can vary. Okay, and what we again see is that when we have a quadratic polynomial where the highest power is 2, then we see that the polynomial can have a maximum of 3 terms, like in this case here. So it has x squared as the first term and minus 2x as the second term and plus 1 as the third term. And we cannot have any other combinations, right? We can have only x squared, x, and x power 0. There cannot be any other x power terms. So therefore, it can have a maximum of 3 terms, or at most 3 terms. So maximum means at most 3 terms for the quadratic polynomial, and it takes the general form of ax squared plus bx plus c. So if you look at this example here, for ax squared, the constant multiplying the x squared term is a, in this case is 1, it's 1x squared. Similarly for bx, the term b, that is multiplying the x here in our example, is minus 2, so b equals minus 2, and the term c corresponds to the number 1, so c equals 1. So again, the general form of the quadratic polynomial is by this expression ax squared plus bx plus c, where a, b and c are all constants and a should not be 0, because if a becomes 0, then the x squared term itself will disappear and it will no longer be a polynomial of degree 2, so therefore it will no longer be a quadratic polynomial. Okay, so the power or the coefficient of the highest power should not be equal to 0 for the polynomial to be called as being that particular degree. Okay, similarly, we have a definition for cubic polynomial, which is a polynomial of degree 3. So again, we have an expression here where the highest degree for the variable is the number 3. So therefore the degree is 3. The highest power or the exponent is 3 for the variable x. So the degree of this particular polynomial is 3. Similarly for this, the highest degree for the variable x is 3. And also here the highest degree for the variable x is 3. So all these are examples of cubic polynomials. Basically it is a polynomial whose degree is 3. And as before, for a cubic polynomial, the number of terms is going to be 4. So in quadratic, the maximum number of terms is 3. In the linear case, the maximum number of terms is 2. And for the cubic polynomial, the maximum number of terms is 4. So we have 3x cubed as the first term, minus 4x squared as the second term, plus 2x is the third term, and the constant is the fourth term. So that's the maximum number of terms we can have. If you look at this expression, it is a cubic polynomial of degree 3, but it has less than 4 terms. So at most means maximum. It cannot have more than that maximum. So it has a maximum of 4 terms. It can have less than 4 terms, but never more than 4 terms. That's number 1. And secondly, it should have a term with the power 3. Okay, only then we call it as a cubic polynomial. So that means the coefficient of x power 3 should not be 0. So in the general form, if we have ax power 3 plus bx squared plus cx plus d, where a, b, c, d are all the coefficients which are constants, we should have that the coefficient of x power 3, which is a, should not be 0. So a is not equal to 0. So this pretty much covers most of the important definitions related to the polynomial with a single variable, and we'll just extend this idea to a polynomial with in the general case. Okay, we have a polynomial with degree, we have seen degree 1, degree 2, degree 3, and so on. In the general case, we say the polynomial has some degree n, and the general expression for a polynomial of degree n is given by this expression. So the highest degree is n, so we have x power n, and all the other degrees will be less than n. So it's x power n minus 1, x power n minus 2, x power n minus 3, and so on and so forth, up to x power 2, x power 1, and x power 0. So each of these variables to the power of the number n and n minus 1 and so on are multiplied with their respective coefficients. So the coefficient of x power n, we will denote it as a power n. The coefficient of x power n minus 1 is an minus 1, and coefficient of x power n minus 2 is an minus 2, and so on and so forth. Similarly, the coefficient of x squared is a2, coefficient of x, we'll call it as a1, and the coefficient of x power 0 is a0. And because we want this to be a polynomial of degree n, the term an, the coefficient of x power n, should not be 0, which is what is mentioned here. So all the coefficients are some constants, and the coefficient of the highest power should not be 0. In this case, we want a polynomial of degree n, so therefore the coefficient of x power n should not be 0. Okay, so this is the general form of the polynomial of some degree n. We can also have polynomials with more than one variable, and we will cover that in later topics. But the focus for the next few videos is going to be polynomials in a single variable. But we can also have polynomials in more than one variable, as we have in this example here. So this is a polynomial expression which has two variables, x and y, not just x. So in the previous cases we had only x or y involved, but in a single expression we have both x and y. So it is x squared plus y squared plus 2xy. So there's a combination of x and y within the same polynomial expression. So we call this as a polynomial in more than one variable. In this case it is a polynomial in two variables, because we have two variables. One variable is x, the other variable is y, and we have an expression using both x and y. Similarly, we have an example here where the number of variables is 3. We have x, we have y, we have z, and other terms using x, y, and z. So we have x into y, y into z, x into z. So the entire expression has three different variables, which are x, y, and z. So this is an example of a polynomial with three variables. So like this we can have polynomials with more than one variable. We have seen an example here for 2 variables, 3 variables. We can also have 4 variables, 5 variables, and so on and so forth. Okay, so now in this video we have seen most of the definitions related to polynomials, the basic definitions in terms of the number of terms, the coefficients of the polynomial, the degree of the polynomial, and some basic terminology like what is a monomial, what is a binomial, what is a trinomial, and also the different degrees of the polynomial. Based on the degree we can say it's a linear polynomial or a quadratic polynomial or even a cubic polynomial, and so on and so forth. Okay, so these are just terms and definitions that we need to remember. But the most important thing that we have to bear in mind is that for an algebraic expression to be called a polynomial, the power of the polynomial should be a whole number. So this n that we have here, n, n minus 1, n minus 2, and so on, each of these must be a whole number. It's a whole numbers extend from 0, 1, 2, 3, 4, and so on and so forth. So if any of the term of the polynomial or the algebraic expression has a power that is not a whole number, in that case that algebraic expression is not a polynomial. Okay, so we'll stop here for today, and in the next video I'm going to do some examples based on these definitions, and then we'll continue our discussion further with this topic.